Say we're told the determinant of a 4 by 4 matrix is equal to -5. And we're given this expression where the A matrix does show up in different forms. And we're asked to find its determinant. And we want to know what this equals to. So we'll see how to go through the different process of solving this in this video. So let's begin solving this problem. But before we do this, notice that this expression has a transpose of a matrix. The inverse of the matrix does show up, and also there's a determinant. So we need to be careful here and remember the properties for when it comes to the transpose of a matrix, the inverse of a matrix in the determinant. Doesn't mean we have to use all three. We'll see if we need to use any of these properties. But one thing to be careful as well is to remember that we're dealing with matrices, not algebra. So we cannot play with the rules that we know from algebra. These are matrices, not algebra. And we're also given the following information. So we know the dimensions of the matrix, and we know the value of the determinant, and it is this negative scalar. So let's begin and see how we could solve this. As a first step, maybe what we could notice right away is the following: that there is a transpose of the expression inside the determinant, and then we take the determinant. And it turns out that there is a nice property from determinants that tells us the following. If we take the determinant of the transpose of some matrix, it just happens that it is in fact equals to the determinant of the matrix. So right away we could get rid of this transpose and put this property to use. So let's call this property 1. And let's see how we could update this expression and possibly simplifying it. So this is equal to the determinant of -1 over 5 times matrix A times matrix A transpose. Everything in this expression is to the power of -1 times A inverse. But the transpose is no longer needed because we used the first property that you see here. So we use this property in this expression. Okay, let's continue the work. So we could then move on to the second step here. So when we multiply two matrices, we could in fact split the result. So this is something that we could notice. So for example, you could think of this entire thing as one matrix and this entire A inverse as another matrix. And there is a property from determinant that tells us if you have the determinant of a multiple, so a matrix A multiplied by matrix B, you could in fact find the determinant of each separately and then multiply them together. So this is also a nice result that we could put to use here in possibly simplifying the result, the expression that we have. So let's call this property 2. And let's use this property here. So we could write this expression as such. We would find the determinant of -1 over 5 like this, A transpose. Be careful not to change any orders here. We have to write it exactly the way it is because we're dealing with matrices, not traditional algebra. So we multiplied by determinant of A inverse. So we split the expression as such because we used the property that is shown to us in that we identified as property number 2. So we used this property to simplify this expression. There's another property that we could put to use is the following. So if we're finding the determinant of an inverse of a matrix, well, this is also equal to 1 over determinant of the matrix. So this is a nice result that we could also put to use here. Both expressions have an inverse. They both have an inverse. Notice the inverse that we have in both expressions. So this is the inverse here. This is the inverse here. So we could put this property, which let's just give it some identifier. Let's just call it property 3 to use. And let's see how we could further simplify this expression. So we could write it as such. We could say that it is 1 over determinant. And by the way, if you don't want to write determinant, you could use the two bars, right? So like as we've seen in before, so the same thing that is used for for the absolute value or the modulus of a complex value. But here I'm going to use determinant just to really tell us that we're dealing with determinants. But you could certainly use these two bars as well. So it's minus 1 over 5 times A transpose, and we get rid of this to the power of minus 1 because we no longer need to find the inverse. We just made it 1 over this expression by using property number 3. We could do the same thing for this one, so we could write it as determinant of matrix A. Okay, so that's nice. So this is, we've applied property 3. Next, what we could do is, well, here for this expression, I could also use, for this expression, I could also use property number 2. I could think of this as two matrices, this being one of them, this minus 5, the scalar minus 1 over 5 times A as being one matrix, and A transpose as being the other matrix. So I could put to use here property number 2. So we could also use property number 2 on this expression. And let's see how we could simplify the result. So this is what we get. We get equal to 1 over determinant of minus 1 over 5 times matrix A times determinant of A transpose, and then of course we carry the 1 over determinant of A that we got earlier. Okay, next what we could do is we could also put to use the property that we showed you, the first property P1. So we could use this property here. So determinant of the transpose of a matrix is in fact equal to the determinant itself. So I could update it like this. In the bottom, I'll end up with two expressions that have determinant of A. So I could write it as such: 1 over determinant of minus 1 over 5. This is my scalar multiplied by matrix A. And then I'll have determinant of A times determinant of A. So in fact, I could just write it as determinant of A squared. So it's a scalar that we get, and then we square it. So let's write the 2 properly. So let's just write it like this. We square the entire result like this. Okay, so this is where we are so far. I don't have enough space, so we need to move on to the next slide, and we'll continue there. Okay, so far we've made some good progress, but we're not done. So there's another property that we could put to use to move forward. It is as such. So if we have the determinant of some scalar k, we multiply it by the matrix A. Well, this is equal to k to the power n determinant of matrix A. What is n? Well, n comes from the dimensions of matrix A. So if it's an n by n, that's where the n comes from. Now this property is true because of the elementary row operations that you could apply to basically find the determinant of a matrix. We showed you this in class. I mean, you can think about it this way. When you multiply a scalar by a matrix, every entry of the matrix will be multiplied by the scalar. And if you want to find the determinant of this matrix that is multiplied by a scalar, you could factor the scalar from every row, and if you have n rows, well, that's where you get your kn. So this property is certainly true, and we can certainly put it to use. There is no requirement on the scalar. As long as it is a scalar, then it's fine. So for example, we could say its element of R 1, so it's a scalar, but it could also be, by the way, a complex value, but let's just say it's element of R, so it's a scalar. And then A, well, this is a matrix, so A is in fact element of R n by n, so this is of course a matrix. Okay, so let's do that. Let's see how we could simplify further this expression. So now we have 1 over, so determinant of a scalar of minus 1 over 5 times A. Well, this is equal to minus 1 over 5. This is our scalar. we put it to the power n. I know it's a 4 by 4, but let's think of this as an n by n, some generic n by n. And I know that the result of determinant of A is minus 5, but let's also maybe call it alpha, alpha being a scalar. For example, being of R1, it's a scalar. So I'm going to use these terms to have some generic expression, and then we could just plug in the 4 and the minus 5 at the end. Okay, so it's we get minus 1 to the minus 1 over 5 to the power n for an n by n matrix times determinant, let me fix this, determinant of A, which is also then multiplied by determinant of A squared. So this ultimately becomes 1 over determinant of A cube. So we could just update it like this. So it's going to be minus 1 to the power n over 5 to the power n determinant of matrix A and everything cube. So I could just rearrange things here. So when I divide by a fraction, it's essentially multiplied by the reciprocal. So I'll have a 5 to the power n in the numerator. In the denominator, I'm going to have 1 to the power n and determinant of matrix A cube as such. Okay, so now, well, I could just plug in, instead of determinant of A, I could just call it alpha so that it's a bit slightly nicer looking. So 5 to the power n over minus 1 to the power n alpha cube. So this is really our final result that we get, where n comes from the dimensions of the matrix and alpha is equal to the determinant of the matrix. So let's just plug in the values that we have for it. So if n is equal, it's a 4 by 4 matrix, so n it would be 4. So I have 5 to the power 4 over minus 1 to the power 4. Alpha, being the determinant of matrix A, is equal to minus 5. Minus 5 to the power 3. And this simplifies as such. This is essentially equal to 5 to the power 4 over minus 1 to the power 4, which is a plus 1. And then minus 1 cube is just minus. And then 5 cube, like this. And this is essentially equals to minus 5. So this is equal to minus 5. It's just interesting to see that the final answer is equal to minus 5, similar to what determinant of A is. This is just because of the numbers that we have, but ultimately the generic answer is the one that I also boxed here for you. So let's highlight this, and so as you notice, this is the generic answer. So it doesn't mean that for a different dimension you will have different values. It won't always equal to the determinant of A that is shown to you here, which is minus 5. But so I hope you saw how we did the steps, and that completes this video.